For those of you who haven't been here the very first time, the idea of the seminar was to talk about physics and particle physics in particular, but also to talk about tools we are using in physics and particle physics in particular. So one of the tools I'm using is Python, a programming language. Some of you might be familiar with, some of you might not be familiar with. And I want to give you a short presentation on Python. So before I start, I have to say that I'm a physicist. I'm not a software engineer, so please apologize if I do not use necessarily always the correct terminology. Although this is some sort of advertisement for Python, I'm not a Python fanboy. There are many things I do not like about Python, so I'm talking as someone who's using Python whenever it's possible, because for me it makes life so much easier to use Python instead of C++ or Perl or whatever. I have to say that the content of this presentation is not only my content, so I stole most of the stuff from other presentations from Guido van Rossum, Matt Ford, Richard Miller, etc. So if you start Googling for presentations, you might see similar presentations. And this presentation is also not meant to replace a lecture or a course in Python, because we need more time for this. This is really just an overview of what you could do with Python in physics. So with this out of the way, I maybe should start asking, if you're programming, which of the programming languages do you know, or which are you using? Somebody using C++ or C? Yeah. Somebody's using Java or has worked with Java, Perl. Fortran, you're probably too young for Fortran. Somebody using maybe MATLAB. No. Okay. So the outline of this talk is the following. Let me give a short introduction to Python. I mean, there's a lot of things you could say about the origin of Python. I will only give you some short notes on the beginning of Python and the idea behind Python. The second part, this is, as I said, this is not a programming course here, but I still want to give you some ideas how Python looks like when you program. I give you the basics of Python. And the third part, I try to point out the differences to other programming languages, and then we can use to understand why Python might be of advantage if we use it in physics. And then I show you some application in physics, how you can use Python in physics. But let's start with the introduction. So this picture is it's from Guido van Rossum. I'm not sure if he's still with Google, but used to work for Google, and he is basically the inventor of Python. He started this in the 1980s.
Where is he from?
He's Dutch. There are many programming languages on the market, and to give you an overview where Python is located in terms of not application, but usage, this is basically a differentiation of the languages, typical languages, in terms of compilation. You all understand what I say when I talk about compilation? You compile a program into. So on the left side, you have the explicitly compiled to machine code languages like C and C++ and Fortran. And on the right side, you have interpreted languages, Shell and Perl, that are actually not really compiled. Well, strictly speaking, they are compiled into something that can be understood, but we call these languages interpreted because in principle, you have an interpreter that goes line by line through the code. Then in the middle, you have the explicitly compiled to bytecode languages, for example, Java and C#, where you write your program in Java or C#, then you compile it into something that is not machine code, but it's called bytecode. And this bytecode is then executed with an interpreter or with a virtual machine, I should say. The advantage of doing this is that the bytecode works on any sort of architecture. You write you compile it on a Macintosh or on an Apple, and the same bytecode can then be executed on a Windows machine or on any other architecture. This is not the case for C and C++ or Fortran. You have to compile the code on that machine where you want to execute. So then you have somewhere in the middle there, between the explicitly compiled to bytecode machine and interpreted, you have Python. So what Python does is it is compiling the code into some sort of bytecode, but not before you run, but while you run it. So what happens is you execute your Python code, and on the just-in-time compiler, it compiles, basically it translates while you're running the Python code. As you can imagine, this means some overhead, and many people consider this as a big disadvantage of Python. It makes it slower because the compilation is not pre-execution. Some more facts about Python. It's an open source general purpose language, so in principle everybody could participate in writing this Python. You can use it object-oriented, so it has all the features of an OO language, but you can also write it procedural or functional. You have all the freedom. In principle, it's very easy to interface with C or Object-C or Java or Fortran. That's how many people use it. You have existing code in C or in Object-C or in Java, and you use Python basically as a glue language between these different parts of other code. And in principle, you can also interface it with C++. It's a little bit more tricky, but it's possible. And something which I only recently started to really enjoy is the interactive environment. Something, unfortunately, I do not have time to talk about this today. It's called IPython or Jupyter. It's a really nice programming environment for Python. To understand the idea behind Python, people usually start to talk about the philosophy, the Zen behind Python. And this is what, when you Google for the Zen of Python, this list, it's not complete, but there's some other points. This is what usually is showing up. It's actually hard coded into Python. If you can get these points all in the Python package, and it will be printed on the screen. So the idea behind Python, or the programming in Python, is the following. So you want to write beautiful code instead of ugly code. Usually it's considered that explicit coding is much better than implicit coding. So write it out what you want to do. I highlighted the most important ones, what I think. If you have something written, or if you have several versions of one, if you have several ideas of how to do something, use the most simple one. Readability counts. I will show you how Python enforces readability of the code. There are some other points which I don't go through. But the other point which I really like is, if the implementation is hard to explain to other people, then it might be a bad idea to implement it like this. So try to implement it in a way that it's easy to explain, and that's usually the better way to write code. So if you summarize, if you put all these points together, you come to the philosophy of programming and yeah.
There is a bullet point there. Left is better than nested.
Yeah. So everybody knows, for example, if-then-else statements. So.
Golden Jason foi 800 e combate, falou 500.
Fabio, I think you're not muted.
Yeah.
Sorry, wait.
So although it might look like more work to write down an if then else statement in a flat hierarchy, it's much easier to read and much easier to maintain as have a nested if then else statement, probably with some loops, etc. That's meant by this. Flat is better than nested because it adds some layer of complication which is not needed.
And because nested reminded me of exactly like the object-oriented language.
Oh, no. That has nothing to do with object-oriented. It's really the bare bone structure of your code, which is usually better if it's written flat. Explicit, yeah. Something I should have highlighted as well is special cases aren't special enough to break the rules, for example. You have this in many languages that you have exceptions, many exceptions to the rules. And Python tries to avoid this kind of exceptions because nothing is really special enough to make exceptions. Unless there is something where you have to say, okay, it's more practical to do it, then you're allowed to break the rules. Okay. So yeah.
Beautiful is better than ugly.
Yeah.
Is this, you think, related to the indentation of Python?
Yeah.
So that it's
So this was really the really very short introduction to Python and the idea behind Python. Let's look at some Python basics. How does Python look like when you program? I mean, you will be surprised. In principle, there are not so many ways to program something. The actual syntax is very similar to other languages. Before we start, we should talk about the versions. There are several versions of Python on the market. There's a so-called current version, which is 2.7 point something. I don't know what this something right now is. And then there's a newer version of Python, 3.5 point something. This is the latest one. So a few years ago, Python made the transition from version 2 to version 3. However, there was so much code written in version 2 that they kept some sort of backward compatibility, and they kept this up until version 2.7. There won't be any version 2.8. Python will not release new versions of Python 2. If you look at the differences between Python 2 and Python 3, for a beginner who never touched Python, these might look very subtle. They're not, I mean, they are important different. But for a beginner, so if you start writing Python code and you do not have to rely on old Python code from version Python 2, then you better start writing code in Python 3. It's a little bit, as I said, the differences are not big. I mean, Python 3 still allows you to write sort of Python 2 code, but if you start from zero anyways, then why not stick to the new words? So if you want to try this, what I show you, I will assume that Python is installed on your system. And usually this is the case for Linux and Mac OS. It's not the case for Windows. For instructions and the binaries, you go to this website with python.org, and there you can get the binaries to install Python on a Windows machine. So there are two ways of running Python. One is the interactive interface, and this is shown here in the first little picture. So this is my computer called Big Bang, and Carsten is my login. So I simply start Python. I type Python, and then my Python version is 2.7.11, and it's the Anaconda release. I do not use the version that comes with Mac OS. I use Anaconda. And then there's some additional information, and then I get the interactive prompt here, which are three little arrows. So then I can really write. I can use this as like a calculator, for example. So I can put in 3 times 7 plus 2, and Python calculates this right away to 27. And I access this interactive interface with Control D. So this is one way of running Python. You understand, if you want to write something now more complicated with more lines of code, then it's better to put it in a separate file. So for example, I wrote a file with my Python code. It's here, my Python program, and usually the Python extension is py. And you call this, you execute this with Python, and then the name of your program. If you want to make this file actually executable and drop this Python here in the beginning, the very first line of your code should read something like this. That's the environment variable, and sets the path to the Python. So this is the second way of executing Python code, and that's the preferred one if you have long lines of long programs. Let's have a look at a code example. So on the left side, the picture shows you a few lines of Python code. For most lines, you can guess right away what this is. So we have here basically an assignment: x equals 34 minus 23. Comments in Python are done with this pound sign. Here's another assignment where I assign apparently a string to a variable. What you see already is that I do not need to clarify what sort of variable it is. So I don't have to say x is an integer and y is a string. I don't have to say this. Python doesn't require this. It decides while executing the code what sort of variable I'm using here. It's also called duck typing. If it quacks like a duck, it is a duck. If it looks like an integer, it is an integer. And this saves a lot of time. For those of you who program C++, keep in mind every time you want to add a new variable, you have to change the header file, and it's a mess. So the next variable z here is a float apparently. Here, this is how a loop looks like, or not a loop, sorry, an if statement. So if z equals 3.45 or y equals hello, then I have this column here, and followed by the column are 2 lines which are executed if one of the statements is true. So what you see is that first of all, logical operators are words and or not, so it's not a symbol. Comparisons are done with 2 equal signs, not 1 equal sign, similar to C++. And then I have here the typical statement of the if statement. And then I have here 2 statements, print x and print y. This is the basic printing command. If I want to print something on the screen, I use print.
How does Python know what's inside the if statement or not?
How does Python know what's inside the if statement?
Yeah. Like, how does Python know that x equals x plus 1 and y equals y plus world are in the if statement, and print x and print y are not in the if statement?
Okay. So first of all, the if block starts with a colon, and whatever is indented here, you see 4 spaces, white spaces. This belongs to the conditional statement. This is executed only if one of the statements here is true. I come to this white space a little bit later on. This is what I mentioned earlier already, that Python forces you basically to write readable code. Okay, this is the very first example. Something. Oh yeah, I should. You see that I can use the plus sign for different purposes. Here I add a 1 to an integer apparently, and here I use plus to concat to strings. So the operator plus is overloaded. I hope this is the right terminology here. The basic data types are kind of obvious. We have integers in this case. Z is an integer, 5 divided by 2. Take into account that the division sign here is an integer division. That means if both numerator and denominator are integers, the result will also be an integer. So it's rounded. So in this case, that will be 2. If you want to force float division,
it's rounding, or does it ignore the fractional part?
it's removing the, yeah, okay, removing the fractional part. If you want to force a float division, you say 5.0 divided by 2 or 5 divided by 2.0. You have to have at least one float either in the numerator or denominator. Floats are assigned like this, so you have a simple float. For strings, you can use single quotes, double quotes, or triple double quotes. They are all the same. There's no difference, basically. Just triple double quotes have the advantage that you can have multi-line strings. If you have very long strings, you can use this triple double quotes. Why do you have several versions of a string? Well, if you want to write the English word don't, D-O-N, quote T, then you can't use apparently single quotes because there is already a little, so then you can use the double quotes. And if you have mixed double quotes and single quotes in one, you can still use the triple quotes to make the string identifiable. Before I continue, one of the biggest differences to other languages is how Python treats variables. And if you want to be really, really strict, Python does not have variables, but names. And what I mean by this is the following. So let's have a look at a typical language like C or C++. So those languages have variables. And you can't really see what I'm writing here. So if I assign a value to a variable, let's use a picture here, int a equals 1, that should be, you can imagine that this is basically putting a number, the number 1, into a box. The box A contains now the value 1. Now I can assign another value to this box. What happens then if I say A equals 2? So I remove the 1 and I put the 2 into this box. If I now assign a second variable to the first variable, what happens then? So if I say I create another variable B and I say equals A, what happens in this case? I make a copy of the value in the first box and put this copy in the second box called B. So now I have 2 boxes, A and B, with 2 versions of the value. This is not very complicated, this is expected, right? Python does it a little bit differently. Python has names. Although, to make it easier, Python programmers speak still about variables, but technically they're names, or name tags, or parcel tags. So when I say in Python A equals 1, what happens is that I attach an identifier or a tag to this object 1. So in this case here, the integer 1 object has a name tag called A. Now I can reassign this name tag to another object. So if I say A equals 2, I take this name tag and put it on another object. In this case, I remove it from the 1 and put it to the 2. I have no idea what happens actually to this 1 here. This object might live on in memory, but I have no way of accessing it anymore. So what happens now if I assign a second name tag to the object? So instead of copying actually the original one, I basically add another name tag. So if I say B equals A, the object that used to have 1 name tag A now has 2 name tags. One is called A and one is called B. And this has dramatic consequences. Let's have some. Let's look at some examples. So it doesn't really matter. Here's some very simple example. I have A equals 2. I assign I assign A to B. And now I say B equals 4, and I print B, and that's what we expected. B is 4. If I print A is 2. So what happened to our name tag analogy? So for simple data types, this works as you want it to work, right? So it makes a copy internally and attaches then the name. But there are more complicated data types, for example, lists. This is shown here in this example. I hope you can read it. So in this case, A is a list. List is like an array. It contains 3 numbers, 1, 9, and 10. We'll come to this list a little bit later, but so this is how you create a list. Now I assign this list to another, or the name to another name. I say B equals A, and I use the append command to add another number. So I say B append 33, and if I print B, then I had 1, 5, 10. That's 1, 5, 10. That's the 3 numbers plus the 33 was added. But if I print A, 33 was also added to 33 was also added to 8. So, and this is due to this naming convention, the tag convention. We say that the list is a mutable object; it can be changed. We will come to a couple of examples later where the difference between a mutable and immutable name is important. So we talked about lists. There are other so-called sequence types. For example, a tuple. A tuple is a simple, in this case, immutable ordered sequence of items. The items can be of mixed types, including collection types. For example, it could be another tuple. A string in itself is also a sequence type. It's also immutable, and it's conceptually very much like a tuple. And then we have seen lists, and the difference between a list and a tuple is that a list now is mutable. What can you do with these kind of things? All 3 sequences or sequence types share much of the same syntax and functionality. Whatever I show you right now is what you can do with one, you can also do with the other one. The key difference is that tuples and strings are immutable, and lists are immutable. So in the example that I will show you now, apply to all sequence types. So how do you define sequence types? So tuples are defined using parentheses and comma. Lists are defined using square brackets. We have seen this in the example before, and commas. And strings are defined using quotes. Here are some examples. You have a tuple. I call this TU, and it contains a number 3. It contains a string. It contains a float. It contains another tuple here and another string. I have a list, basically the same syntax, but you use now square brackets, and I have 3 different strings where I use 3 different versions: single quote, double quote, and triple double quote. So this is how I define them.
I have a question. Like those mutable and immutable objects, is there like a logic behind like to what is gonna be mutable and what is not gonna be mutable, or just something like we have to know, like that lists are mutable?
Yeah. There are special use cases for lists where you want to use lists, and there are special use cases where you want to use tuples.
And the dictionaries, for example, are they mutable?
Dictionaries are mutable.
Mutable.
Yeah.
Okay.
So how do you access now a member of such a sequence? Well, what you use is the square bracket notation. And all sequence types start counting at 0. So the very first member is the member number 0. This is similar to C and C++, but different, for example, to Fortran, where the first member is 1. So for example, here, my original tuple, 3 ABC, 4. If I want to access the second member, I say print TU1, and it tells me ABC. That's the one. Here's my list. I want to print the second member. I did this. I can do the same for the for string, and I get an E. That's all as expected. I can also use negative indices. When I use a positive index, I start counting from the left, starting at 0. If I use a negative index, I count from the right, starting with -1. To give you an example, so I have the tuple here as before, and if I print the second one, I get ABC. If I print index -1, I get K, which is basically the last one. I can do something that's called slicing. You can return a copy of your container to the subset of the original members. So in this case, if I say print TU1 to 4, and I get basically the elements from 2 to the third image, to the fourth image. A, B, 4.56, and so what's the difference between lists and tuples? So lists are slower, but they are more powerful because they are mutable. So lists can be modified because they are mutable. And there are a lot of operations which I can't show you momentally. So you can reverse the order, like a function for that. You can sort the order, you can count, you can remove members, you can get the index of members, you can insert members, many more. Tuples don't have these options. They are mutable, but they are much faster. Sometimes you have the need that you have a list in your code, but what you need is a tuple. So you can use the tuple function. You can create a tuple from a list and vice versa. So the last data that I want to show you is a dictionary. Dictionaries are exactly what the name says. It's a dictionary. It stores a map between a so-called key and a set of values. Keys can be any immutable type, and values can be any type. So in principle you can use tuples as keys, and you can't use a list. So a single dictionary can store values of different types. You can modify, define, modify, and view, lookup, and delete the key value pair in the dictionary. I have some examples how this looks like here. So first example, you have a dictionary where you have 2 keys and 2 values. So the key is here user, and the value is total. You have another entry with the key password and the value 1, 2, 3, 4. You can just access now the element that has the key user, and Python returns me the value which is total. You can do the same for the password key, and Python returns the value 1, 2, 3, 4. But if I try to access now something which is not a key but a value, it will complain. So key error. Bozo is not a key, it's a value.
So you can only access the dictionary that you have with the key,
yeah,
not with an index like D0.
No, there is no particular order here. There's no sequence really.
Yeah.
So what happens here? I have a dictionary here. Again, user related to Bozo and password 1, 2, 3, 4. I can give this particular key a new value, say clown, and if I print now the dictionary, it has changed. I can add a key value pair by just say okay D, and then I add a key ID is 45. Now I have 3 key value pairs. I can remove particular key value pairs by using the delete. I can clear the complete dictionary. If I'm interested in a list of keys, I can ask for the keys, give me all the keys, and it returns a list of all the keys. I can do the same for the values. Or I can do the same for all the pairs. So it's a very handy, very powerful way of storing information. We talked about white space before, and I want to spend one slide on white space. White spaces are meaningful in Python. They're not necessarily meaningful in other languages. So to end a line in Python, you need the new line, the character. In principle, I think it's C or C++. You can write your code in one line. Never end a line. We don't use any braces in Python to mark blocks of code. So those of you who write C or C++, you might know this, that if you have an if statement, you start the conditional statement, no, not the conditional statement, the block with open braces, right? But where do you put the open braces? At the end of the condition or in the next line? Both are totally valid, absolutely allowed. Some people say you have to do it one way, other people say you have to do it the other way. Everything is fine as long as you work alone on the program. If you work on a bigger program with several people, you mess up your code because you can be sure that several people have several ideas how this should look like. The compiler doesn't care about this, but if you're working with the code, you should care about this, and it makes code more complicated. So what does Python? Well, Python requires you to indent the code. So when you have a block starting of code after an if statement or in a loop, you have to indent. You have to use white space. So let's look at an example here. So here's a for loop. For line in file is basically a loop over all the lines in the file. And whatever should happen here is now indented by 4 white spaces. Then you have another conditional statement. It's called the try. I don't want to go into details, but you start a new block here again, indented by 4 white spaces. Here you have an if statement inside this indent, and you get another indent, and so on. So in principle, it makes the code much more readable because you have no choice here. You have to do this. Everybody codes the same way. And you do not spend any time discussing on where to put braces to make code more readable. Last thing I want to show you in the basic is the function. Functions are defined with a def statement. It creates a function and assigns a name to it. Functions usually contain a return statement, and return statement sends a result back to the call. You don't have to put in a return statement if you don't want to. Python will put in one in for you and returns the statement 0 or none. Arguments to a function are passed by assignment. Arguments and return types are not declared. So here is the definition of a function. You have to provide a name, and then in parentheses you provide a list of arguments. Column, and then you have again your white space. You can have your statements, whatever your function is supposed to do, and the return value. Here's an example of a multiplication function. So the name of the function is times. It takes 2 arguments, x and y, and it returns x times y. So it now is, you can see there is no type declared here. So if you want to use this function, in principle, you could pass 2 strings to this function, and it will not work. So it's your responsibility to check that the types make sense. Python will not do this for you. That's the downside of that type. So as I said, arguments are passed by assignment. It depends in principle if these arguments you're passing are mutable or immutable. The best thing is I show you an example. I have here a function that takes 2 arguments, x and y. If I pass to this function x an integer, then x becomes here a local copy. So the outside variable, that what used to be x, does not change. However, if y in this case is part of the list, lists are mutable, and I say inside this function, the first element of the list should be high now. This changes the object also outside of this function. Again, difference in mutable and immutable. So last thing I'll show you some function gotchas. Such as all functions have return values even if you don't provide one. Function without a return statement returns the special value none. There's no function overloading in Python, so two different functions can't have the same name. That's different to C++, where you can have two different functions with the same name as long as they have different arguments. In Python, it's not possible. However, functions can be used in Python as any other data type. So functions can be functions of can be arguments of functions. They can be return values of functions. You can assign a function to a variable, and you can assign. They can be part of a list. And I'll show you here how this works. I define three functions: f of x and y, which returns basically the sum of x and y. I have one function called g, which returns the product. And I have a function h, which returns the ratio as long as h is not 0. Here I create a list of functions, and I put in the list f, g, and h using the square brackets notation. I define two variables a and b, and then I loop over the function in this list. This is a loop over this. And I can print function, I can say print function AB, and function now goes to F, G, and H. It's very easy, a very handy way of accessing several functions. Okay, that's everything I want to show you about the basics. There are many things I have not covered, as I said, this is not a Python course. So I haven't talked about object-oriented programming, classes, inheritance. You can all do this. I haven't mentioned modules at all. In principle, this is how you share code. Introspection. Each object in Python knows information about itself that you can request to print on the screen, for example. I haven't talked about iterators, generators, and comprehension. There's a huge standard library that comes with Python, and many other things which I just don't want to mention here because it's outside of the scope of this talk. Let's talk a little bit about the differences to other languages. And I hope that after we talk about this, we can understand why it might be beneficial to use Python. So nobody has programmed in Java yet, but if you compare Java with Python, let me assure you the following. This is something I pulled off the Python web page for this. True. So Python programs are usually expected to run slower because they're compiled in time and not before they run. But they also usually take less time to develop. So if you write Python code, you're usually much faster. So whatever you lose in time when executing probably slower Python code, you might save in developing and maintaining the code. Python programs are usually 3 to 5 times shorter than equivalent Java code because you don't have this overhead of declaring variables, etc.
Can Python always replace Java, or because I imagine there are cases that's better to write to Java?
I'm pretty sure that there might be some pathological cases where you can only gain if you use Java and not Python. And I don't see any reason right now to use in physics for sure now. But there might be some server client programming problems that only can be done in Python because there are certain libraries which I don't know. But in Python, it's definitely not speed. if you're interested in speed, you would not program in Java anyways, because then you would go to C++, or you would go to C, or even Fortran. If you're really interested in high-speed performance computing, then nobody would use Java. So Perl was on the other hand of the spectrum, a purely interpreted language, and in principle, Perl and Python come from the same background, and they have many similar features, but different philosophies. So when you use Perl, what you want to do usually is you want to scan files, you use regular expressions, you're looking for special things inside a file, you want to generate reports on computer states, etc. That's what you use Perl for. Python actually emphasizes the program methodology, data structures, object orientation. Although I think right now you can also have OO and Perl. Anyway, so in principle, you can do most of the stuff Perl can do in Python as well. But if you're really interested in this core task of Perl, then you would not use Python either. But this is basically some system administration, for example. Then you would use Perl. For the daily usage, I don't see any reason not to use Python, especially since Python can do so much more than Perl.
Was Perl developed before or after?
I think it's much older, yeah. So most of you know C++. In principle, everything I said about Java applies here as well, but it's even more severe. So Python code usually is 5 to 10 times shorter. And I'm okay. This is not what I say, but there are some people, some hardcore Python programmers, and they say, okay, one Python program I can finish in 2 months, what 2 C++ programmers can't complete in 1 year. Oh, sure. But that's what Python people say. And Python usually shines as a glue language to combine components written in C++. That's kind of something where you have Python and C++ missing.
Yeah.
Yeah. So in our experiment, for example, where we use a C++ framework, software framework, we use Python to steer the different parts of the program because it's so much easier to do this with Python.
And there are things that Python can really not do, but only C++, because of the slow.
Okay, yeah. If you
heavy programming.
Yeah. So yes. Yeah. Again, if you want to look at speed, and if you're interested in, you have to what do I say? C++ out of the box is much faster for sure, but it's much more error prone. It's basically a gun pointed at your head all the time. So it's very easy to shoot yourself. So you have to be very careful what you use C++. So, but there might be the use case where you really have to have a very fast execution. When you don't have to give up on Python there. You can precompile. You can force Python to precompile into C, and then it's very compatible to C and C++. So I listed here some pros and cons of Python. There are definitely more pros and cons. So, but some very big disadvantages of Python are it's not really elegant if you're interested in parallel computing and concurrency programming. Something which, if you're interested in data mining and stuff like that, is probably a big issue. It's possible to do this in Python, but right now it's not very. Server client programming doesn't really require Python if you're working in this side. And meta programming, like it's done in this, is not a strong side of Python. Yeah, it's not, that's not, that's,
Okay,
no,
let's not get there.
I have to spend 2 more slides.
Yeah.
But these are all 3 points which are not really touching particle physics. So forget about this. On the other side, the advantages of Python, they do really touch programming and physics. So for example, time-wasting methods of size, I mentioned the blocks and the credit breaks. They don't exist here. The easy way of doing something in Python is usually the correct way. And you can become very productive with Python very quickly, even at the beginning. That does not mean that Python is not a powerful language. I mean, it's very easy to do something for beginners with Python. At the same time, Python is very powerful for experts.
I think Python is very intuitive.
Yeah. So usually the first thing that, if you don't know how to do something in Python, and might have an idea, or usually the first thing that comes to mind is 90% of the cases the right thing. So let me give you some examples where you can use Python in physics, because you might want to say, I have a special use case and I can't use Python. So for example, you want to manipulate big data structures, like big tables of data. This is just a small table here. There's something called Pandas, which is a software library written for Python to manipulate data and do data analysis on these big tables. And everybody who has to do this kind of things, they know what I mean when I say data alignment. These kind of tables might not be very symmetric. I mean data alignment. You can do time series. They have time series functionality. This is something very interesting if you do a measurement and you record something every second or every day or something. This is a very powerful tool to do this sort of analysis of time series. You can group and you can pivot. You can change the structure of the table. This is all foreseen in Python. Many more things. And everything is Python. You might not be interested in data manipulation, but you might want to be interested in big arrays and matrices. Then NumPy, or NumP sometimes, might be handy. It's an extension that was written to add support for large multidimensional arrays and matrices, along with a very large library of high-level mathematical functions to operate on these arrays. So here's an example. If I have 2 lists and I want to multiply these 2 lists element-wise, then I do it in Python the following way. Here's a loop over an array of, I ask the array A, how long are you, length A, and I loop from 0 to the length of it. I have an empty list C, and I add to this list the product element Y. This is something very slow in Python. Python is not very strong when it comes to loops. In NumPy, you have this sort of syntax, and it's super fast. It's like this. It's written in C. It can't get much faster. And this is just one example of 2 very simple.
And this has physics applications. This
oh yeah, I mean,
matrices.
Yeah. Oh, in principle, you can use the matrices to do linear algebra problems, solving linear equations, inverting things. Okay, you're interested in scientific computing, not so much in matrices and stuff. Then SciPy is your friend. It's a library for Python that is written for optimization, finding minima, maxima, linear algebra, integration, interpolation. It comes with special functions, fast Fourier transformation. You can do ordinary differential equations and many more. Everything in Python.
Is it like a MATLAB but for Python?
It's SciPy and MATLAB for Python, and well, it has the features of MATLAB. Yeah. If you're more interested in visualizing results or visualizing data, then you want to look at matplotlib. It's a plotting library for Python, and I don't list what matplotlib can do. I just show you some examples of those plots that matplotlib got done with matplotlib. So you can really do fancy things. So some of you might use root. Those of you who do not use root or don't know what it is, we can't go into this. But those of you who use root say, well, I cannot use Python because I have to use root, and root is the C++ framework. What should I do? I cannot switch to Python. Actually, you could if you want. There's something called rootpy, which is a Pythonic layer on top of tyroot. Tyroot is an interface to root. So you can write root code now with Python syntax. So, and that's basically what I do right now. I use Python as my daily driver. So if I look for a specific file, I scan through files with Python. If I want to analyze data, I use Python as well. This rootpy does not recreate root. Root is still under the hood. I just use it using Python code. It's not a new analysis framework. It's just a library that one analysis framework can use. And I cannot only use root. I have now, because I use Python to access root, I can also access at the same time the pandas, numpy, and scipy packages, and all the other packages. So something which I cannot do if I only use root. I have no access to pandas or numpy. So, and there's much more. So it took me yesterday 3 minutes to just Google for Python packages. There's something called QTIP that's used for simulation of dynamics of open quantum systems. SymPy library for symbolic mathematics. So scikit-learn machine learning in Python. AstroPy, a single core package for astronomy in Python. Cosmotalk, a Python version of the cosmology software. I have no idea what that is, but apparently it's the same. ALPS, algorithms and libraries for physics simulation. SumPy, a package for solar physics, and so on. There are hundreds of packages out there. People use Python everywhere. So that's basically everything I wanted to show you about Python. And something I haven't mentioned yet, why it's called Python. It's not Python because of the snake, it's called Python because of Monty Python. The inventors of Python thought programming should make fun, and Monty Python was their hero. So to summarize, here's a plot that I pulled from the internet yesterday. It shows the most popular coding languages of 2014. As you can see, Python is with 30.3%, the most popular language. And I hope you got an idea why that is. It's very powerful. So yes, Python is yet another programming language. There are cases where you should not use Python in physics, particle physics. But there are not many, and you really have to construct them. For your daily life, Python can do everything you need. Yes, it is slower than most of the other languages, but at the same time, developing Python code is so much faster. You save a lot of time there, and it's not easy to say where you lose more time. Beginners make progress fast. It's very easy to write something in Python. It doesn't take a lot. And if there's interest, we can think about offering a Python tutorial lecture in the next semester, something like a 2 or 3 day course with some hand-on tutorials. And yeah, that's basically it I wanted to show and talk about. If any questions, we have a lot of time, I think. Yeah, questions. You can also ask in Portuguese. I think I would understand if this would be something that, or you can ask later, send me email. Super, everybody is happy, that's great. Then I'm going to close the session for today. Just a quick reminder, in 2 weeks our seminar will be with Petra Hünkelmeier. She is a professor of physics at Michigan Tech University, and she will talk about cosmic ray physics with HAWK. HAWK is an experiment that's put together in Mexico, and she will show us how this works and what they are doing there. And yeah, she's doing cosmic rays for quite some time now, and yeah, I'm looking forward to that. If you're interested, please stop by. Thank you. Thank you, Father, for joining.
Thank you.